Fluid catalytic cracking is one of the most important conversion processes used in petroleum refineries. It is widely used to convert the high boiling, high molecular weight hydrocarbon fractions of petroleum crude oils to more valuable gasoline, olefinic gases, and other products. Cracking of petroleum hydrocarbons was originally done by thermal cracking, which has been almost completely replaced by catalytic cracking because it produces more gasoline with a higher octane rating. It also produces byproduct gases that are more olefinic, and hence more valuable, than those produced by thermal cracking. The feedstock to an FCC is usually that portion of the crude oil that has an initial boiling point of 340 degrees Celsius or higher at atmospheric pressure and an average molecular weight ranging from about 200 to 600 or higher. This portion of crude oil is often referred to as heavy gas oil or vacuum gas oil. The FCC process vaporizes and breaks the long-chain molecules of the high-boiling hydrocarbon liquids into much shorter molecules by contacting the feedstock, at high temperature and moderate pressure, with a fluidized powdered catalyst. In effect, refineries use fluid catalytic cracking to correct the imbalance between the market demand for gasoline and the excess of heavy, high boiling range products resulting from the distillation of crude oil. As of 2006, FCC units were in operation at 400 petroleum refineries worldwide, and about one-third of the crude oil refined in those refineries is processed in an FCC to produce high-octane gasoline and fuel oils. During 2007, the FCC units in the United States processed a total of 5,300,000 barrels per day of feedstock, and FCC units worldwide processed about twice that amount. Flow diagram and process description. The modern FCC units are all continuous processes which operate 24 hours a day for as long as 3 to 5 years between scheduled shutdowns for routine maintenance. There are several different proprietary designs that have been developed for modern FCC units. Each design is available under a license that must be purchased from the design developer by any petroleum refining company desiring to construct and operate an FCC of a given design. There are two different configurations for an FCC unit, the stacked type where the reactor and the catalyst regenerator are contained in a single vessel with the reactor above the catalyst regenerator, and the side-by-side type where the reactor and catalyst regenerator are in two separate vessels. These are the major FCC designers and licensors: side-by-side configuration, CB&I, ExxonMobil Research and Engineering, Shell Global Solutions, Axon/Stone and Webster Process Technology currently owned by Technip, Universal Oil Products currently fully owned subsidiary of Honeywell, stacked configuration, Kellogg Brown and Root. Each of the proprietary design licensors claims to have unique features and advantages. A complete discussion of the relative advantages of each of the processes is beyond the scope of this article. Suffice it to say that all of the licensors have designed and constructed FCC units that have operated quite satisfactorily. Reactor and Regenerator. The reactor and regenerator are considered to be the heart of the fluid catalytic cracking unit. The schematic flow diagram of a typical modern FCC unit in Figure 1 below is based upon the side-by-side configuration. The preheated high-boiling petroleum feedstock consisting of long-chain hydrocarbon molecules is combined with recycled slurry oil from the bottom of the distillation column and injected into the catalyst riser, where it is vaporized and cracked into smaller molecules of vapor by contact and mixing with the very hot powdered catalyst from the regenerator. All of the cracking reactions take place in the catalyst riser within a period of 2–4 seconds. The hydrocarbon vapors fluidize the powdered catalyst, and the mixture of hydrocarbon vapors and catalyst flows upward to enter the reactor at a temperature of about 535 degrees Celsius and a pressure of about 1.72 bar. The reactor is a vessel in which the cracked product vapors are separated from the so-called spent catalyst by flowing through a set of two-stage cyclones within the reactor, and the spent catalyst flows downward through a steam stripping section to remove any hydrocarbon vapors before the spent catalyst returns to the catalyst regenerator. The flow of spent catalyst to the regenerator is regulated by a slide valve in the spent catalyst line. Since the cracking reactions produce some carbonaceous material that deposits on the catalyst and very quickly reduces the catalyst reactivity, The catalyst is regenerated by burning off the deposited coke with air blown into the regenerator. The regenerator operates at a temperature of about 715 degrees and a pressure of about 2.41 bar. The combustion of the coke is exothermic and it produces a large amount of heat that is partially absorbed by the regenerated catalyst and provides the heat required for the vaporization of the feedstock and the endothermic cracking reactions that take place in the catalyst riser. For that reason, FCC units are often referred to as being heat balanced. The hot catalyst leaving the regenerator flows into a catalyst withdrawal well where any entrained combustion flue gases are allowed to escape and flow back into the upper part to the regenerator. The flow of regenerated catalyst to the feedstock injection point below the catalyst riser is regulated by a slide valve in the regenerated catalyst line. The hot flue gas exits the regenerator after passing through multiple sets of two-stage cyclones that remove entrained catalyst from the flue gas. The amount of catalyst circulating between the regenerator and the reactor amounts to about 5 kg per kg of feedstock, which is equivalent to about 4.66 kg per liter of feedstock. Thus, an FCC unit processing 75,000 barrels per day will circulate about 55,900 tons per day of catalyst. Distillation column. The reaction product vapors flow from the top of the reactor to the bottom section of the distillation column where they are distilled into the FCC end products of cracked naphtha, fuel oil, and OFF-gas. After further processing for removal of sulfur compounds, the cracked naphtha becomes a high-octane component of the refinery's blended gasolines. The main fractionator OFF-gas is sent to what is called a gas recovery unit where it is separated into butanes and butylenes, propane and propylene, and lower molecular weight gases. Some FCC gas recovery units may also separate out some of the ethane and ethylene. Although the schematic flow diagram above depicts the main fractionator as having only one side cut stripper and one fuel oil product, many FCC main fractionators have two side cut strippers and produce a light fuel oil and a heavy fuel oil. Likewise, many FCC main fractionators produce a light cracked naphtha and a heavy cracked naphtha. The terminology light and heavy in this context refers to the product boiling ranges, with light products having a lower boiling range than heavy products. The bottom product oil from the main fractionator contains residual catalyst particles which were not completely removed by the cyclones in the top of the reactor. For that reason, the bottom product oil is referred to as a slurry oil. Part of that slurry oil is recycled back into the main fractionator above the entry point of the hot reaction product vapors so as to cool and partially condense the reaction product vapors as they enter the main fractionator. The remainder of the slurry oil is pumped through a slurry settler. The bottom oil from the slurry settler contains most of the slurry oil catalyst particles and is recycled back into the catalyst riser by combining it with the FCC feedstock oil. The so-called clarified slurry oil or decant oil is withdrawn from the top of slurry settler for use elsewhere in the refinery, as a heavy fuel oil blending component, or as carbon black feedstock. Regenerator flue gas. Depending on the choice of FCC design, the combustion in the regenerator of the coke on the spent catalyst may or may not be complete combustion to carbon dioxide CO2. The combustion airflow is controlled so as to provide the desired ratio of carbon monoxide to carbon dioxide for each specific FCC design. In the design shown in Figure 1, the coke has only been partially combusted to CO2. The combustion flue gas, containing CO and company, 2, at 715 degrees Celsius and at a pressure of 2.41 bar is routed through a secondary catalyst separator containing swirl tubes designed to remove 70 to 90% of the particulates in the flue gas leaving the regenerator. This is required to prevent erosion damage to the blades in the turbo expander that the flue gas is next routed through. The expansion of flue gas through a turbo expander provides sufficient power to drive the regenerator's combustion air compressor. The electrical motor generator can consume or produce electrical power. If the expansion of the flue gas does not provide enough power to drive the air compressor, the electric motor generator provides the needed additional power. If the flue gas expansion provides more power than needed to drive the air compressor, then the electric motor generator converts the excess power into electric power and exports it to the refinery's electrical system. The expanded flue gas is then routed through a steam-generating boiler where the carbon monoxide in the flue gas is burned as fuel to provide steam for use in the refinery as well as to comply with any applicable environmental regulatory limits on carbon monoxide emissions. The flue gas is finally processed through an electrostatic precipitator to remove residual particulate matter to comply with any applicable environmental regulations regarding particulate emissions. The ESP removes particulates in the size range of 2 to 20 AA micrometer from the flue gas. Particulate filter systems, known as fourth-stage separators, are sometimes required to meet particulate emission limits. These can replace the ESP when particulate emissions are the only concern. The steam turbine in the flue gas processing system is used to drive the regenerator's combustion air compressor during startups of the FCC unit until there is sufficient combustion flue gas to take over that task. Chemistry. Before delving into the chemistry involved in catalytic cracking, it will be helpful to briefly discuss the composition of petroleum crude oil. Petroleum crude oil consists primarily of a mixture of hydrocarbons with small amounts of other organic compounds containing sulfur, nitrogen and oxygen. The crude oil also contains small amounts of metals such as copper, iron, nickel and vanadium. The elemental composition ranges of crude oil are summarized in Table 1, and the hydrocarbons in the crude oil can be classified into three types: paraffins or alkanes, saturated straight-chain or branched hydrocarbons, without any ring structures, naphthenes or cycloalkanes, saturated hydrocarbons having one or more ring structures with one or more side-chain paraffins, aromatics, hydrocarbons having one or more unsaturated ring structures such as benzene or unsaturated polycyclic ring structures such as naphthalene or phenanthrene, any of which may also have one or more side-chain paraffins. Olefins or alkanes, which are unsaturated straight-chain or branched hydrocarbons, do not occur naturally in crude oil. In plain language, the fluid catalytic cracking process breaks large hydrocarbon molecules into smaller molecules by contacting them with powdered catalyst at a high temperature and moderate pressure, which first vaporizes the hydrocarbons and then breaks them. The cracking reactions occur in the vapor phase and start immediately when the feedstock is vaporized in the catalyst riser. Figure 2 is a very simplified schematic diagram that exemplifies how the process breaks high-boiling, straight-chain alkane hydrocarbons into smaller straight-chain alkanes as well as branched-chain alkanes, branched alkanes and cycloalkanes. The breaking of the large hydrocarbon molecules into smaller molecules is more technically referred to by organic chemists as scission of the carbon-to-carbon bonds. As depicted in Figure 2, some of the smaller alkanes are then broken and converted into even smaller alkanes and branched alkanes such as the gases ethylene, propylene, butylenes, and isobutylenes. Those olefinic gases are valuable for use as petrochemical feedstocks. The propylene, butylene and isobutylene are also valuable feedstocks for certain petroleum refining processes that convert them into high-octane gasoline blending components. As also depicted in Figure 2, the cycloalkanes formed by the initial breakup of the large molecules are further converted to aromatics such as benzene, toluene, and xylenes, which boil in the gasoline boiling range and have much higher octane ratings than alkanes. In the cracking process, carbon is also produced, which gets deposited on the catalyst. The carbon formation tendency or amount of carbon in a crude or FCC feed is measured with methods such as microcarbon residue, Cohn-Rudson carbon residue or Ramsbottom carbon residue. By no means does Figure 2 include all the chemistry of the primary and secondary reactions taking place in the fluid catalytic process. There are a great many other reactions involved. However, a full discussion of the highly technical details of the various catalytic cracking reactions is beyond the scope of this article and can be found in the technical literature. Catalysts. Modern FCC catalysts are fine powders with a bulk density of 0.80 to 0.96 gram per centimeter 3 and having a particle size distribution ranging from 10 to 150 AA micrometer and an average particle size of 60 to 100 AI 1/4 m. The design and operation of an FCC unit is largely dependent upon the chemical and physical properties of the catalyst. The desirable properties of an FCC catalyst are good stability to high temperature and to steam, high activity, large pore sizes, good resistance to attrition, low coke production. A modern FCC catalyst has four major components: crystalline zeolite, matrix, binder, and filler. Zeolite is the primary active component and can range from about 15 to 50 weight% of the catalyst. The zeolite used in FCC catalysts is referred to as phage acid or as type Y and is composed of silica and alumina tetrahedra, with each tetrahedron having either an aluminum or a silicon atom at the center and 4 oxygen atoms at the corners. It is a molecular sieve with a distinctive lattice structure that allows only a certain size range of hydrocarbon molecules to enter the lattice. In general, the zeolite does not allow molecules larger than 8 to 10 nm to enter the lattice. The catalytic sites in the zeolite are strong acids and provide most of the catalytic activity. The acidic sites are provided by the alumina tetrahedra. The aluminum atom at the center of each alumina tetrahedra is at a +3 oxidation state, surrounded by 4 oxygen atoms at the corners, which are shared by the neighboring tetrahedra. Thus, the net charge of the alumina tetrahedra is -1, which is balanced by a sodium ion during the production of the catalyst. The sodium ion is later replaced by an ammonium ion, which is vaporized when the catalyst is subsequently dried, resulting in the formation of Lewis and Bra-NSTED acidic sites. In some FCC catalysts, the Bra-NSTED sites may be later replaced by rare earth metals such as cerium and lanthanum to provide alternative activity and stability levels. The matrix component of an FCC catalyst contains amorphous alumina, which also provides catalytic activity sites and in larger pores that allows entry for larger molecules than does the zeolite. That enables the cracking of higher boiling, larger feedstock molecules than are cracked by the zeolite. The binder and filler components provide the physical strength and integrity of the catalyst. The binder is usually silica sol and the filler is usually a clay. Nickel, vanadium, iron, copper and other metal contaminants, present in FCC feedstocks in the parts per million range, all have detrimental effects on the catalyst activity and performance. Nickel and vanadium are particularly troublesome. There are a number of methods for mitigating the effects of the contaminant metals. Avoid feedstocks with high metals content. This seriously hampers a refinery's flexibility to process various crude oils or purchase FCC feedstocks. Feedstock feed pretreatment. Hydrodesulfurization of the FCC feedstock removes some of the metals and also reduces the sulfur content of the FCC products. However, this is quite a costly option. Increasing fresh catalyst addition. All FCC units withdraw some of the circulating equilibrium catalyst as spent catalyst and replaces it with fresh catalyst in order to maintain a desired level of activity. Increasing the rate of such exchange lowers the level of metals in the circulating equilibrium catalyst, but this is also quite a costly option. Demetallization. The commercial proprietary demet process removes nickel and vanadium from the withdrawn spent catalyst. The nickel and vanadium are converted to chlorides, which are then washed out of the catalyst. After drying, the demetallized catalyst is recycled into the circulating catalyst. Removals of about 95% nickel removal and 67 to 85% vanadium have been reported. Despite that, the use of the demet process has not become widespread, perhaps because of a high capital expenditure required. Metals passivation. Certain materials can be used as additives which can be impregnated into the catalyst or added to the FCC feedstock in the form of metal organic compounds. Such materials react with the metal contaminants and passivate the contaminants by forming less harmful compounds that remain on the catalyst. For example, antimony and bismuth are effective in passivating nickel and tin is effective in passivating vanadium. A number of proprietary passivation processes are available and fairly widely used. The major suppliers of FCC catalysts worldwide include Albemarle Corporation, W. R. Grace Company and BASF Catalysts. The price for lanthanum oxide used in fluid catalytic cracking has risen from $5 per kilogram in early 2010 to $140 per kilogram in June 2011. History. The first commercial use of catalytic cracking occurred in 1915 when Armour M. McAfee of Gulf Refining Company developed a batch process using aluminum chloride to catalytically crack heavy petroleum oils. However, the prohibitive cost of the catalyst prevented the widespread use of McAfee's process at that time. In 1922, a French mechanical engineer named Eugene Jules Houdry and a French pharmacist named Each Prudhomme set up a laboratory near Paris to develop a catalytic process for converting lignite coal to gasoline. Supported by the French government, they built a small demonstration plant in 1929 that processed about 60 tons per day of lignite coal. The results indicated that the process was not economically viable and it was subsequently shut down. Houdry had found that Fuller's earth, a clay mineral containing aluminosilicates, could convert oil derived from the lignite to gasoline. He then began to study the catalysis of petroleum oils and had some success in converting vaporized petroleum oil to gasoline. In 1930, the Vacuum Oil Company invited him to come to the United States and he moved his laboratory to Paulsboro, New Jersey. In 1931, the Vacuum Oil Company merged with Standard Oil of New York to form the Saucony Vacuum Oil Company. In 1933, a small Houdry unit processed 200 barrels per day of petroleum oil. Because of the economic depression of the early 1930s, Saucony Vacuum was no longer able to support Houdry's work and gave him permission to seek help elsewhere. In 1933, Houdry and Saucony Vacuum joined with Sun Oil Company in developing the Houdry process. 3 years later, in 1936, Saucony Vacuum converted an older thermal cracking unit in their Paulsboro refinery in New Jersey to a small demonstration unit using the Houdry process to catalytically crack 2,000 barrels per day of petroleum oil. In 1937, Sun Oil began operation of a new Houdry unit processing 12,000 barrels per day in their Marcus Hook refinery in Pennsylvania. The Houdry process at the time used reactors with a fixed bed of catalyst and was a semi-batch operation involving multiple reactors with some of the reactors in operation while other reactors were in various stages of regenerating the catalyst. Motor-driven valves were used to switch the reactors between online operation and offline regeneration and a cycle timer managed the switching. Almost 50% of the crack product was gasoline as compared with about 25% from the thermal cracking processes. By 1938, when the Houdry process was publicly announced, Saucony Vacuum had 8 additional units under construction. Licensing the process to other companies also began and by 1940 there were 14 Houdry units in operation processing 140,000 barrels per day. Your next major step was to develop a continuous process rather than the semi-batch Houdry process. That step was implemented by advent of the moving bed process known as the Thermofor catalytic cracking process, which used a bucket conveyor elevator to move the catalyst from the regeneration kiln to the separate reactor section. A small semi-commercial demonstration TCC unit was built in Saucony Vacuum's Paulsboro refinery in 1941 and operated successfully, producing 500 barrels per day. Then a full-scale commercial TCC unit processing 10,000 barrels per day began operation in 1943 at the Beaumont, Texas refinery of Magnolia Oil Company, an affiliate of Saucony Vacuum. By the end of World War II in 1945, the processing capacity of the TCC units in operation was about 300,000 barrels per day. It is said that the Houdry and TCC units were a major factor in the winning of World War II by supplying the high-octane gasoline needed by the air forces of Great Britain and the United States for the more efficient higher compression ratio engines of the Spitfire and the Mustang. In the years immediately after World War II, the Houdry flow process and the airlift TCC process were developed as improved variations on the moving bed theme. Just like Houdry's fixed bed reactors, the moving bed designs were prime examples of good engineering by developing a method of continuously moving the catalyst between the reactor and regeneration sections. The first airlift TCC unit began operation in October 1950 at the Beaumont, Texas refinery. This fluid catalytic cracking process had first been investigated in the 1920s by Standard Oil of New Jersey, but research on it was abandoned during the economic depression years of 1929 to 1939. In 1938, When the success of Hydrol's Euro unregistered trademark S process had become apparent, Standard Oil of New Jersey resumed the project as part of a consortium of that include 5 oil companies, 2 engineering construction companies and a German chemical company. The consortium was called Catalytic Research Associates and its purpose was to develop a catalytic cracking process which would not impinge on Hydro's patents. Chemical engineering professors Warren K. Lewis and Edwin Gilliland of the Massachusetts Institute of Technology suggested to the CRA researchers that a low-velocity gas flow through a powder might lift it enough to cause it to flow in a manner similar to a liquid. Focused on that idea of a fluidized catalyst, researchers Donald Campbell, Homer Martin, Edgar Murphy and Charles Tyson of the Standard Oil of New Jersey developed the first fluidized catalytic cracking unit. Their U.S. patent number 2,451,804, a method of and apparatus for contacting solids and gases, describes their milestone invention. Based on their work, M.W. Kellogg Company constructed a large pilot plant in the Baton Rouge, Louisiana refinery of the Standard Oil of New Jersey. The pilot plant began operation in May 1940. Based on the success of the pilot plant, the first commercial fluid catalytic cracking plant began processing 13,000 barrels per day of petroleum oil in the Baton Rouge refinery on May 25, 1942, just 4 years after the CRA consortium was formed and in the midst of World War II. A little more than a month later, in July 1942, it was processing 17,000 barrels per day. In 1963, that first Model I Fcc unit was shut down after 21 years of operation and subsequently dismantled. In the many decades since the Model I Fcc unit began operation, the fixed-bed Hydro units have all been shut down as have most of the moving bed units while hundreds of Fcc units have been built. During those decades, many improved Fcc designs have evolved and cracking catalysts have been greatly improved, but the modern Fcc units are essentially the same as that first Model I Fcc unit. Note: all of the refinery and company names in this history section have changed over time by mergers and buyouts. Some have changed a number of times. See also, oil refinery, petroleum, cracking, catalysis, references. External links: Valero Refinery Tour Description and Diagram of Power Train, CD Tech website discussion of Lummus Fcc and hydrotreating of catalytically cracked naphtha. The Fcc Network, recovery of company from Fcc using the Coprism process, North American Catalysis Society, Fluid Catalytic Cracking, CFD simulation of a full-scale commercial Fcc regenerator.